Hey everyone, how's it going? My name is Jason Voegele. I work at Basho Technologies, where I'm an Erlang developer working on the React database. And today I'm going to be talking about Dialyzer, which is a type checking tool for Erlang and Elixir. So, leading into that, I want to talk about holy wars first. These are these incredibly productive online discussions that people have about holy religious topics, and usually ends up in a lot of vitriol and name calling. And if any of you here are old enough to have been on Usenet back in the day, you may have witnessed or even participated in some of these discussions. So like the granddaddy of them all, of course, is Emacs versus VI, and which is the world's one true text editor. And everybody has their opinions on this, whether they're right or wrong. Vim is the answer, of course. So, but there are other people who have found some compromises here. So you've had some efforts like Vile and Evil and Spacemax that have tried to kind of bring the best of both worlds together, use the nice runtime platform of Emacs with the modal editing of Vim and so forth. And that's been really successful. And another one I used to witness a lot was the old tabs versus spaces argument. Now, this is probably dating me because nobody formats their code with tabs anymore, right? So the younger programmers here probably didn't even realize this was a thing. So spaces won that battle. And finally, you got your Linux desktop environments. Used to argue about whether KDE or GNOME was the future whenever Linux finally took over the desktop. And well, this argument basically became irrelevant because the era of Linux on the desktop never really happened. So well, there's probably a few holdouts in the group, so I apologize, no offense. And one of the biggest holy wars in programming circles has always been static versus dynamic typing, right? I've been programming for a long time, and I've actually been on both sides of this battle. I've argued both sides. I've been productive in static languages and dynamic languages both, and I think there are good reasons to choose either one. And interestingly, last year I was at Strangeloop, and Gary Bernhardt did a talk there called Ideology, and he was kind of breaking down the underlying belief systems of people who fall on either extreme of this issue. So he made the case that you have type bigots, which are people that maybe you're hardcore Haskell programmers, and maybe a lot of people here in the audience go to the AGDA talks and whatnot. They kind of have this belief that my type system tells me everything I need to know, and if it compiles, ship it. It's got to be correct, right? And then on the other side of the coin, you've got maybe your average Ruby programmer who, the testing culture is really strong in Ruby land, and so they say, I've got all these tests that prove my system is correct, so what do types really add for me? So those are the kind of extremes you'll see on this position. And today I want to introduce kind of a middle ground approach, which is called gradual typing. And the idea here is that you're kind of grafting a static type system on top of an existing dynamic language. And it's a type system where some of your variables and functions have type declarations and some don't. It's completely up to the programmer to decide which ones that makes sense for. Now, why would you want to do this? So if you're working in a dynamic language, you probably appreciate the looseness and flexibility that offers. You like things like duck typing. You don't want to spend a lot of time like appeasing your compiler and convincing it that you're right when you know perfectly well that what you're doing is correct. But on the other hand, there are some definite benefits that static typing definitely provides. That includes like having a tool to check your program for correctness and consistency, and maybe even more importantly is the aid and documentation that type declarations can provide. So if you have type declarations in your program, it makes it that much easier to read and document. So that's the idea of gradual type checking. This talk is going to be about how you do that in Erlang and Elixir. So historically, Erlang has been a dynamically typed language, right? But I'm going to argue that it's also a strongly typed language. And now people mean different things when they say strongly typed or weakly typed. But all I mean when I say that is it doesn't allow you to combine types in nonsensical ways. So the example here is the number 5 plus the string 2. Well, that's an error in Erlang. It doesn't allow like nonsense like JavaScript, like an array plus the number 2. That gives you something, who knows what, but it's not an error, right? So that's why I would argue that Erlang is actually a strongly typed language, even though it's runtime dynamically type checked. Now, Erlang does have some nice features that provide sort of rudimentary type safety support, and those include like pattern matching and guard sequences. And while they're useful and beneficial, those are checks that are done at runtime as well. So we're still completely in the dynamically typed universe there. Over the years, there have been several attempts to try to add static typing into Erlang. The most famous of which is the one I've noted up here is in 1997, Marlowe and Wadler tried to graft a full static type checking system onto Erlang. And it was unsuccessful, like all the other attempts to put true static typing into Erlang, for the basic reason is that they were trying to make it too strict. So if you imagine at this time, Erlang's a very old language, and even in 1997, it had been around for a dozen years or more, right? And there were already existing production systems that had been running flawlessly for years, and Erlang had a great reputation for fault tolerance, being very robust, and now you've got this type checker that's saying, this is all wrong. And it's been running flawlessly in production, but I don't like it, so it's going to reject it. So that was the basic problem with all of the static type checking implementations in Erlang, was that they were too strict. So all of those failed, but something that came up out of the ashes with that was this tool called the Dialyzer. Horrible name. I'm not going to try to justify that, but that's what they call it. It's the discrepancy analyzer for Erlang programs. What it is, it's a static analysis tool that performs type checking. And what I mean by a static analysis tool is it's not a part of the compiler, nor a part of the runtime system, but it's a separate tool, maybe like find bugs or lint, that you run against your source code, and it will try to find discrepancies in your type usages. It features type inference, meaning that it can analyze your code and try to figure out what types your program entities are, but it also allows for optional type specifications, which is where the gradual typing comes in. So it allows you to put type specifications on your functions if you choose. The type checking model that it uses is it's an optimistic model based on something called success typings. So what does that mean? Well, here's a definition from the original paper that describes the type model for Dialyzer. It's a whole lot of words. I'm not going to try to interpret that. Basically what it means, it's an optimistic system that never cries wolf. And what I mean by that is that if it cannot definitively prove that something in your program is incorrectly typed, it's going to assume you know what you're doing and move on and not flag an error. So that's in contrast to the previous attempts in Erlang to use strict type checking, which failed for the reasons we mentioned earlier. This was a much more successful model because it was optimistic and worked with kind of existing Erlang code that wasn't written with static type checking in mind. Okay. So that's kind of like where Dialyzer came from. It's out of the Erlang world. Moving forward, I want to start talking about Elixir. Now, Elixir's the new hotness, what all the kids these days are using, maybe to the chagrin of some of the old Erlang curmudgeons. I may or may not work with that guy. So if you're not familiar with it, Elixir is a newish language created by Jose Valim. It's tightly integrated with the Erlang virtual machine known as Beam. And all the code examples going forward from here are going to be in Elixir. So, now the first one I want to look at is how the type inference system works for Dialyzer. I mentioned you can put type specifications on your functions, but even if you don't, it's going to try its best to infer the types of your functions and variables that you use. So let's take a look at how that works. This first function we see here at the top is a simple add function. Takes in an x and a y as arguments, and in the body of the function simply adds those two together using the plus operator. Now in Erlang, the plus operator is defined to work only on numbers. It doesn't do like string concatenation or anything like that. There's no operator overloading. So we know that the plus symbol means take two numbers and add them together. Now using that knowledge, Dialyzer can then infer the type signature for this function. Because x and y are used on either side of the plus operator, it knows that both of those must be numbers. And furthermore, since the plus operator is defined as producing a number as a result, that's what the return type is inferred as. The next function, divide, is similar. It's a little bit different in that we're using the division operator in the body of the function. That also takes numbers as arguments, but specifically produces floating point number as output. So it doesn't do like truncation or integer division. We know that it returns a floating point number as output. So Dialyzer is able to infer a slightly more specific return type on that function. Okay, and then one final, slightly trickier example here is a logical AND function. This is you don't need to write your own AND function in Elixir. It's got one for you, but if you chose to write one, this is one very logical way to do it, and that is just to use pattern matching on the arguments that are passed to you and return either false or true depending on what type of arguments you got. Okay? So the first one is saying the AND function defined for false and anything else returns false. Likewise, the AND function with any value and false as second parameter is also false. And it's only when you have true as both your parameters that returns true. So what does Dialyzer do with type inference for this one? Well, obviously the return type is going to be Boolean because in all three of these cases, it's either false or true. And those are all Booleans, of course. But if you look at the input parameters and what it inferred, it really couldn't make much sense of it. It's listed as any. You might expect that to be Boolean there, right? Well, the problem is the way we define these functions is that we're saying false and anything else evaluates to false. So we could say false in the number 42, that returns false. Or you could say false in the string Joe and false also returns false. So since we're allowed to legally pass in those values to this function, Dialyzer has no recourse but to say the type is any. But what if we wanted to be more specific and insist that our AND function used only Boolean values? Well, we can use type specs for that. So function type specs use the @spec notation. You just list out your signature for your types for your function on the @spec line. So let's jump down to the AND example we were just talking about here. It's the same definition for the AND function. All we've done here is add a type spec above it that says that the input arguments must be Boolean. And now having done so, this will kind of override the type inference mechanism by Dialyzer, and it will use the types that you declared for your function rather than what it could infer based on its usages. Okay, so we've seen what type specs look like. What kind of types can you put in your type specs? Well, there's a whole range of them. All of your basic types that are built into the Beam and Elixir are available as types. Booleans, characters, atoms, strings, all sorts of things. You can even use literal values, like the literal value true or the atom OK. It's common in Erlang and Elixir for functions to return the atom OK to say everything went all right. Well, you can encode that into your type spec just by putting that atom in there as if it were a type. And you've got top and bottom types, should you ever need those. Any is the top type, and if you don't know more specifically what type you're dealing with, then you can use any. There's a variety of ways to encode numeric types, including integer and float keywords, or you can use the number keyword, which is kind of like the super type of those. It's literally defined as integer or float. If you want to be more specific about the range of values in your numbers, you can say whether you want a positive integer, a negative integer, a non-negative integer, or even a specific range of integers. If you have a function that can take only a very specific range of numbers, like the number of months in a year, for example, then you can use this range syntax to say that 1.12 is the type that this function would accept. And there are a whole bunch of collection types, of course, lists being probably the most commonly used one. If you want to put lists in your type signature, there's a few different ways to do that, using either just the keyword list or this like open and close square brackets syntax there. That will tell you that you have a list, but it doesn't say anything about what's inside of the list. If you want to say what's inside of the list, you just use the parameterized version of those, include the type in parentheses in the first case or inside the brackets in the second case. And you can even say that you want your list to be non-empty by using one of those syntaxes there. Tuples are another commonly used type. You can specify those using the keyword tuple or the curly brace syntax. And what's really nice about tuples is that you can get very specific in defining what you want your tuples to look like in your type signature. So this example here that has curly brace atom binary curly brace, that means it's a tuple with exactly two values in it, the first of which is an atom and the second is a binary. And you can get very specific with those. Maps are a newer feature in Erlang. I guess they've been in Elixir from the beginning, but these are key value collections, and the syntax for those is this curly brace preceded by a % sign. But what's kind of cool about this is that if you want to specify what types your keys are and what types the associated values are, there's a syntax for doing that. So if you want a function that takes a map where the keys are atoms and the values are integers, that's the syntax you would use for that. And of course, you can combine these in any arbitrarily complex way you want. So you can nest maps within lists, within tuples, and so forth and so on, arbitrarily nested. And of course, Elixir is a functional language. Functions are first-class citizens. You can pass them as arguments to other functions or return functions from functions. And because of that, you need a way to represent that in your type system. And there's a nice simple syntax for doing so. It's basically your, within parentheses, a list of your parameter types, followed by your return type after an arrow. So we've got a few examples here of different arities of functions, so functions that take different numbers of arguments, and what that looks like. And even in the case where you don't really care about how many arguments the function takes, you just want to specify, give me a function that returns a Boolean, you can use this like triple dot syntax to express that concept. All right, this all wouldn't be very useful unless you could define your own types, of course. So I've got a little example here to show how defining your own types works and how you can use those in specifying the types for your functions. So this is just a simple module that kind of defines playing cards, a deck of playing cards. So first thing we're doing here is defining a type suit. And if you were in this room earlier for the algebraic data types talk, this will look like the OR type that was described there, and that's because this is basically an ADT. What we've got here is we're listing the possible values for a suit in a deck of cards. So you got spades, hearts, diamonds, or clubs. So we're using those literal values in the type definition. So those are atoms in Elixir, or you would call them symbols in Ruby. Now, why might you want to define these as a type? If you're just going to be passing these literal values around in your program, what benefit does it really provide to encode them as a type in your type system? Well, if you've done any Ruby or Rails programs, you know that Ruby is completely dynamically typed and uses these symbols everywhere to pass around like option arguments. And what's very easy to do is like misspell one of them. And you have a little typo and say you misspell diamonds. And Ruby, who knows what's going to happen if you do that. In the best case scenario, you'll get an immediate crash and know to fix it. But worst case scenario is it goes unnoticed for a really long time and something disastrous happens later. If you encode it into your type system like this will be caught before you ever ship your code, because the type checker will catch that for you. Okay, so the value type is similar. We're saying the value on the card is a number in the range of 2 to 10, or it's jack, queen, king, or ace. And then having those two types defined, we can define what a card is. We're defining a card here as a tuple, the first element of which is the suit of the card, and the second element of which is the value. So we're defining what a card is in terms of the type system we've created here. So how do we use that? We've got a function down here called suit. And what this suit function does is basically takes in a card as an argument and extracts the suit out of that structure. So we've got a type spec that says this suit function takes the card type as its one argument, which we've defined above, and it returns a suit. So we said that what a card is a tuple with a suit and a value in it. So we can then use that knowledge inside the body of the function, knowing that when we're in there, we know we have a valid card, right? So if we go down to the bottom here, we look at this broken function. Here we can see an error that the type checker will actually catch. That's a pretty easy error to make. We're calling the suit function with what looks to be a card, but if you look closely enough, you'll see that they're swapped. So the value is listed before the suit in this example. So according to our type specification, what we've got, that tuple we've got there is not actually a card. And when we try to call suit with that structure, the type checker will warn about that and give you an error. Now, there's a lot of really other cool stuff in Dialyzer that I don't really have time to get into, but if you are working in Elixir or Erlang, I'd encourage you to check these things out. You can do some really cool stuff with parameterized types, polymorphic types, and one of my favorite things is opaque types. This kind of brings the object-oriented notion of encapsulation into the functional Elixir world, allow you to do some sort of data hiding or information hiding. Lots of other cool features there. But just want to wrap up by kind of bringing it back to the beginning of the discussion where we're talking about gradual typing is a good compromise between static typing and dynamic typing, right? And does Dialyzer really provide that for Elixir and Erlang? And I'm going to say yes and no. Maybe the Haskell programmers in the group or people who are used to really strict type systems might be a little disappointed in some errors that Dialyzer cannot catch that the Haskell type system would. But you got to remember that that's kind of by design because of the nature of Erlang being a production system that was dynamically typed from the beginning, and we're kind of grafting an optimistic type checking system on top of it. So that being said, it doesn't catch as many errors, but the ones that it does flag, because of its optimistic nature and it never cries wolf, if it does flag an error, then that means that's definitely something you should take a look at, and it's probably a bug in your code or one of your type specs. And furthermore, just having the type specs even on your functions just makes it that much easier to read and for future programmers to deal with it. I would highly encourage you to use this if you're working in Elixir and Erlang, even if it maybe is not as strong as the Haskell type system. It's definitely going to save you a lot of trouble and probably find some bugs in your code. We've actually had real cases at Basho where type checks have actually found bugs in our code that slip through the unit testing cracks, and so that is not uncommon. So definitely worth checking out and incorporating in your program. So I think that's all I had. I don't know if we had any questions or if we have time for that. Yeah.
Back on the other, you're showing that you had the types declared inside the module.
Mm-hmm.
If somebody else wanted to refer to those, is that a possibility, or would you have to just declare it outside the scope?
Yes, so they're exported to the outside world unless you declare them as private. So like in Erlang, you actually have to explicitly export them to be used outside. But by default in Elixir, those are all visible. So it's, you'd basically be saying playing cards.suit in this example here from the outside world. And that's kind of what opaque types get into, is they allow you to refer to those types from the outside world but not know the details of them. So that's kind of a cool thing that didn't really have time to get into. Yep.
What if your data is coming from the input? How does Dialyzer handle runtime at the input? Or does it know one of the errors you can't check?
Yeah, it basically assumes that you know what you're doing, and it's only doing like the strict type checking on like literal values that it can figure out from the structure of your code, and anything that comes from the outside world is, I don't know what this is, so I'm going to either treat it as an any or just assume that what you told me about it is true. Yeah.
Is there a paper describing the type system in like a formal semantics sense?
There is. I forget the name of it, but the authors are these guys here, Lindahl and Sagonis. You can Google that, and they have several papers actually on the type model that's used in Dialyzer. Yes?
I know there are some reports for gradual to Ruby as well. I was wondering if this was inspired by that, or do you have any
This system is pretty old, so it came about in the late 90s, and so like Ruby existed by then, but just barely, right? So I think Ruby's probably been inspired by this.
That's pretty new, actually.
Yeah. Yeah.
So you mentioned that you could specify literals
Mm-hmm.
in the text. Is that's to say I'm expecting just this exact value?
Yeah, you could say that you're expecting that, or it's probably more commonly used as return type specifications. Like I mentioned the example of this function returns the atom okay, and that happens a lot. Or this function returns a tuple where the first element is okay, and the next element is the value that you really wanted to get out of there. So you'll see that more often than in the argument specifications. Anything else? Yeah. Compound literals. I'm not sure if I know what you mean by that.
Well, so like if you are thinking through lists, could you say that the result has to be the sum of the links of the two lists?
I don't know how you would express that. No, I don't think so. Like you can use literal values in other structures, right? So I mentioned the ranges, for example. So you can say that it's a literal integer in this range, or you can use literals in like these compound declarations where you've got like tuples that contain specific numbers in a specific position or something like that. So, right, so that's something that would like happen at runtime, right? So, yeah. Mm-hmm.
So literal values helps in some way to pattern match.
Yes, yeah. So,
Make some kind of optimization or something.
say again?
Let's make some kind of optimization or.
Yeah, I don't know that there would be any optimizations done because like this isn't really built into the compiler in any way, so it's kind of a separate thing. So the tool is really smart about Erlang syntax, so it kind of understands the pattern matching and like having multiple function heads that have different patterns of arguments, and that's what there's a feature in Dialyzer that I didn't really get to talk about that's overloading the type specs. So you would have an overloaded type spec if you have a function that has multiple heads that match on different patterns. So, okay. Yeah.
So if you didn't provide any kind of types or those annotations that you had,
Mm-hmm.
how useful is just the inference on its own?
It's decent. It's a good starting point, right? So if you inherit a code base, or heaven forbid you produce a code base that doesn't have any type annotations on it, that's a good place to start just by running the Dialyzer tool. It's going to go in and check for consistency of usage, right? Because like we said, it can infer that some things are numbers based on the fact that you're doing arithmetic operations on them, or that you're reading from the outside world that comes in the form of a binary, for example. So there's some information that it can glean on its own. And there's even a separate tool that ships with Erlang called Typer. And what that will do is it will run that type inference process, and instead of trying to put out warnings or errors as its output, it will generate the type specifications for you, and then you can just like paste those into your modules. So it'll scan all your functions and print out what its inferred type for that function was. So that one only works in Erlang, unfortunately, not in Elixir.
But sorry, this is for both Erlang and Elixir.
Everything except the Typer tool that I just mentioned. That last tool, Typer, is only Erlang. It doesn't exist in Elixir. I think there's someone who started up a project to do the Elixir version of that one. Okay, so I think I've hit the end of the time here, so thank you. Appreciate it.